Okay, 4-3. Okay, our first new distribution is called a geometric distribution. I should have said probability distribution, but they're all probability distributions. This one answers questions like, how many trials does it take until the first success occurs? So how many trials does it take until the first success occurs? So, do you know exactly how many trials you're doing? No. So let's just talk about it for a second here, the difference between a binomial question and a geometric question. Say we're flipping a coin. A binomial would say, flip a coin 10 times, and then it could ask the question like, find the probability of getting 6 heads out of those 10 trials. So I know exactly how many trials I'm doing, it was 10, and I was looking for 6 successes. On a geometric, it might say, how many times do you have to flip a coin until a head occurs? So it could say, what's the probability that the first head you flip happens on trial number 4? So it's where the first success is happening. Not how many successes, but where the first success happens. Keep that in your head. So, the conditions for a geometric distribution. The first condition is that a trial is repeated until the success occurs. Each trial is independent of the next. What does that mean? What happens on the first trial doesn't affect the second one's sample space. And the probability of a success has to be the same on each trial. So, we've got a formula and a program, we're going to stick with program, for giving the probability that the first success occurs on trial number X. So, formula and program. Oops, I can spell formula. Formula and program that give the probability that the first success happens on trial number X. Okay, before I start, what's the smallest value X can take on here? Knowing that X is a trial number. 1. We can't have 0 here, because in binomial, X represented the number of successes, and we could have no successes. Here, it's the trial number of the success, so it has to start at 1. So here, X must start at 1 and then go up. either happens on the first trial, second trial, on and on and on. Okay, so the probability of the first success happening on trial number X is given by the probability of a single success multiplied by the probability of a failure raised to the X minus 1. Pretty easy formula if you had to do it by hand, but again, it's built in. You're going to find that under our distributions, GeoMet PDF, under distributions, yep, GeoMet PDF. Well, if you take a look at the by hand formula, how many values are we going to have to feed the GeoMet PDF? Do we have to feed it 3? Just 2, because it can figure out the Q. So we're still going to, we first feed it the P, and then we feed it the trial number. So X is the trial number of the first success. P is the probability of a success. And then the GeoMet CDF, again, that C stands for cumulative. It automatically adds probabilities together. So you don't have to do a bunch of PDFs and add them yourself. Just a little time saver. You still feed it P and X. Where do you think it starts adding from? The first trial, added to the second trial, added to the third trial, all the way up through whatever X number you put in there. So that adds probabilities. This is supposed to be a little time saver. I think I'm going to give you both of them first and then mix up the examples to see if you can tell which is which. I think I'll do that. Does that sound good? Okay. Yeah. Quick. Okay, the last distribution is called a Poisson distribution. Like poison. Poisson distribution. A Poisson distribution answers the question, what is the probability that a specific number of occurrences takes place within a given unit of time or space. So I could ask a question like, based on my past history, what's the probability that I take 5, 6 days next school year? So I'm looking at 5 occurrences over a span of a school year, based on my past record. So it's how many occurrences happen within a given unit of time or space. The condition? X represents the number, represents the number of occurrences in the time or space interval the probability of the event is the same for each interval. And the occurrences are independent of each other. Okay, now we're ready for our formula and program. And the formula and program will answer for the probability of exactly X occurrences is given by this. It's the mu. What is mu again? It's the mean. It's what normally happens. It's what's the average number of occurrences. Occurrences are, like I would look at what's the average number of sick days I took per year over the last 20 years. That's my average. So that's a mu. So it's what normally happens for that time interval, raised to the x times e, the constant e. You saw this in advanced algebra. It's like 2.71 blah-de-blah-de-blah. You have an e button on your calculator, I'll show it to you. Raised to the negative mu, all divided by x factorial. So the mu is the mean number of occurrences per interval, and that's what makes this one, a Poisson, easy to pick out, because it's the only one of the three where they have to give you a mean in it. The average number of occurrences, or the average number of times this happens. They have to say it in the problem somewhere. You automatically know it's a Poisson. Okay, E is a constant. It's approximately 2.718. You have an E button on your calculators, right here on the graphing one. It's like pi. Pi is a constant, so is E. We just don't use E as often. But all the scientific calculators have them and the graphing calculators. But we don't do it by hand anyway. We're going to use the Poisson PDF. It's the program that goes for this formula. This formula is built into the PDF program.